Alright. Hello everyone. And welcome to week 4. Today's topic is language models, or more specifically only BERT basically. So I will go over some of the natural language processing basics. So how do we handle language at all? Then the architectures that we're going to use. So a short recap of transformers. So I assume most of you kind of know how transformers work because you all took deep learning, yes? But I'll tell it to you again anyway because I think it's important. Then finally, yeah, the language pretext tasks, everything together then will be this model BERT, which was like the first, I'd say, proper representation learning model for text. Okay. But first, some questions for you. So far you only basically have worked with images, in this course anyway. So regarding deep learning or representation learning, how do images differ from text? So, yeah.
They scale in 2 dimensions.
Sorry?
They scale in 2 dimensions.
The images, you mean?
Yeah.
Yeah, images are 2-dimensional. Yes?
They have a definite shape. Text can have several shapes.
Yes. Contact here. Let's say like variable length. Okay, they can of course have also different shapes, but you can resize images. You can't really do this with text. Resizable, you write like this? Probably not. So it's 1D, this is 2D. What else? Yes?
Is the range in which the input values are defined in text is like tokens.
Yes.
This is between 0 and 1.
Yeah. So like it's like inherently numerical continuous, so the different pixels have different intensities, which can be easily described with a real number, with a float number. And here, well, it's more difficult. That's basically properties of the data themselves, but then what can we do with the data? For example, the things that you learned last week, those pretext tasks you talked about, could you do this with language? So it's, yes?
I mean, you couldn't rotate the text.
Yeah. I mean, kind of a loaded question, but generally all the transformations that you can do with images are not easy with text. So images you can scale and rotate and blur and color jitter, and you can do transformations with text. You can use other models or use like handcrafted sentences that have like the same meaning, but like generally transformations are very hard. Transformations, basically no transformations. Okay, and finally, I think are the downstream tasks. So what are like the typical downstream tasks for images?
Classification.
Yeah.
Segmentation.
Yeah, classification is like probably the most popular one. Segmentation is already like a little bit difficult with representation learning because like per pixel. but most things that you want to do with images, you want to learn some, can be basically described as classification. And I don't know if you have some NLP experience, but I would like some typical NLP tasks. Yes?
Predicting the next word.
Yes, for example, but...
Or the sentence. Translation.
Sorry?
Translation.
Translation, yes. Language translation, which is already more difficult, and I'll just go ahead. So I think, yeah, we basically have everything. And here are some of the tasks. Translation, so there we have the input, the sequence, and the output is a sequence in a different language of potential different length. And text to speech, so text is usually more multimodal than images, so it's connected with more different domains than images. So you have data sets that combine text and images, you have data sets that combine text and video, data sets that combine text and speech. So text is like the common core domain, basically. If you want to learn something multimodal. Sentiment analysis, so what's like the mood of a sentence, which is again classification. Summarization, and like maybe interesting named entity recognition. So there's the task, what is like the subject that the sentence is talking about and where is it referenced to? So if I say the tree is, I don't know, an oak, it is very tall, then the subject would be tree, but also like the it in the next sentence, which refers to the tree. Okay, but before we can go further about all that stuff, we have to talk about tokenization first. So I won't go into detail there because that's not the focus of this lecture. But basically, we assign each word to a token, and some more or less common words are split into multiple tokens. So here we have the sentence, does ChatGPT understand language? And the words does understand language are all very common, so they each get their own token here. But ChatGPT is not a common word, and it's becoming more common maybe. So this gets split like in two tokens, GP and split token, chat, GP and T, and like these hashtags here mean that that is like a sub-word token. So and there are lots of different ways to do this. This one is from the word piece tokenizer, which basically takes a whole very large corpus, a data set of words, and looks at which words are very common and assigns them to each to their own tokens, and then which words are a little bit less common, and then splits them into two tokens. Basically, it splits the words in tokens in such a way so that you get the least number of tokens for a typical text. So it basically does a kind of compression on the text. And then each token gets assigned a number. And the word piece tokenizer has around 30,000 tokens, I think. So each text gets turned into a sequence of numbers from 0 to 30,000, roughly. And because it splits uncommon words into smaller words, it can handle all kinds of new words and words in different languages and other things that it hasn't seen in the training data. So, but you don't need to know any details about that. Just that text get turned into a sequence of numbers. Okay. So then how do we deal with our what input and output should our representation model take? So for images, you usually have something like this. So we have our representation function G. An image has like the shape 3 times H times V, the W. So 3 color channels, height and width. For each, you can have representation for each pixel. And then you compress this into some representation in some d-dimensional representation. Each image gets represented as a single vector of some dimension. Now here we must take a variable length of vectors. So now we already had vectors. Somehow we turned our list of numbers into vectors. How we do this, I'll talk about later. But our function needs to take a variable length of vectors. So that's what this star here represents. So RD star is basically the set of all vector lists of different length. So this is basically like RD star is the it's like the union of RD times L for L from 0 to infinity. That's what our input is. Sequence of vectors of arbitrary length. So what then should our output be? What would be a good representation shape for such an input? Any ideas? So for images we have just a single vector. Would this be a good idea for text? I mean, the way I ask this, you can probably guess that the answer is no, it's not a good idea, but why do you think such a representing a text as a single vector might not be a good idea? Yes?
Because the text can have variable length, maybe that if it gets long, maybe it would work to have finite, just a single vector.
Yes, so basically, yeah, that's one point. So basically, like the information density in a text can vary much more than in an image. And the other thing is you have to think about the tasks. So things like named entity recognition are like token level tasks. So you want to predict which tokens exactly refer to which entity. And if you have only one vector as a representation, this is very difficult, basically impossible. So that's where basically we want the output also to be a sequence of vectors. So we want for each token a representation output here, Z1 to ZL, which we use for like token level tasks, like named entity recognition, but we also want like an extra output, Z0, I call it here, which is like a summarization for the whole text, which we then will use for not token level tasks, for tasks that use the whole input, like sentiment classification. So tasks that take the input and take like a finite number of output. Alright, so how can we deal with variable length inputs in general? So what kind of neural networks architectures do work? Yes? Yes, RNNs are recurrent neural networks. So, if you don't know, they basically work like this. So you have your network here. Basically, you have your tokens here, x1 to xl. You give this network has 2 inputs and 2 outputs. So the input at the first step is basically, let's say 0. It gets 0 here, and the token here. This is some kind of network, and it outputs the representation z1 and a hidden state, which then goes into the same network with the same parameters again, but with the second token, which then outputs z2 and the hidden representation, which is used in the next step, and so on. And then the last output is like the hidden state of everything, z0. So there are some problems with this. Maybe some of you already know if you talk about this in deep learning. What are some problems with RNNs? Yes?
If the information only flows from left to right, but in text there can be some things in the end which is related to the beginning, so
Yes.
it's not taking care of that.
Yes, that's one thing. Yes.
Yeah, for tokens that are far away in the sentence, it's hard to let them share information.
Yes. Yeah. So there are like the 2 most important ones. Like the long-term interactions between words isn't really given, but of course in like sentences, the first word and the last word can be very related. And there are other things like the vanishing gradient problem, because it has to go to the same network every time. It gets very little gradient basically at the end, and there are ways that solve this, like LSTMs, long-term short-term memories, and what are called groove cells, but they don't solve like the problem of long-term interactions. And also, the information about the whole text, the Z0, only basically comes out at the end, and therefore there tends to be very little information about the beginning in this last hidden state. So it forgets a lot. And other things that you can do are one-dimensional convolutional networks. So basically the same as with images. You can have like a kernel which takes some fixed number of tokens and combines them somehow into the output. And you can do this over multiple layers if you want. But this has the same problem with long-term interactions. So the way to solve this basically is to learn the interaction, to learn which words are related to which other words. And this is done by attention. And you can combine the attention mechanism with RNNs, or you can just only use attention, and then you come to transformers. Okay, so I'll explain the attention mechanism real quick. So, I mean, you said you're all kind of familiar, so I won't take too much time. Where will I do it? Basically, it works like this. So you have your input sequence x1 to xl, and they're all d-dimensional. then you compute values. They're called V1 to VL, and let's say they're D QKV dimensional. This stands here for query key value. And they can compute it in any manner from the input, but usually this is just a simple linear layer. So Vi is equal to WV times Xi, where this is just a matrix. And you apply the same matrix for all vectors in the input sequence. Then you want to compute the output. So Zy as a weighted sum of the values of the other tokens. And let's call the weight alpha ij. And the weights should sum up to 1. So the idea is that for words that are very related to this word, this value should be high, and for other words, this should not be high. So again, there are lots of ways to compute this. Basically, this is a function that takes the xi and xj as input and spits out some number, the attention score. But again, this is usually just done with a linear transformation. So we compute the query Qi, which is the linear transformation WQ times Xi, and the value, which is not the value, the key Kj, which is equal to Wk times Xj. So we have 3 matrices in our attention mechanism. We Wv, Wq, and Wk. And then we compute the attention between x1, xj, and this is just the dot product. I hope this is still on camera. And we usually scale this by the dimension. I mean, there are different ways to do this. And then we apply softmax to this to scale it, to basically make probabilities of this, and then we get the weights. And that's also basically what's, this is basically the vectorized form. Of course, you can put all the input into one matrix by just stacking them and then applying the matrix to this, and then they call this Q and K, and you do this operations. And to then get some more a more expressive layer, we do this basically multiple times. This is then called multi-head attention. For each, you have some number of heads, say 16, and for each of the heads, basically, we have a different matrix. So we add in subscript everywhere. And the dimension dkv is then usually the total dimension, so the input dimension divided by number of heads. So if the input dimension, if each of these input tokens has like size 512, and we have 16 heads or 8 heads, then here the output dimensions of these layers will be like 64 each, and then we concatenate them get back to 512 and add another linear layer to each token, and we have turned our sequence of vectors of size 512 into another sequence of vectors of also size 512. Then we add another short MLP on top, so just a two-layer network, three-layer network with one hidden dimension. And this is then a transformer block. And we just stack them how often we want, and we get a transformer. And also important, just that works and learns are like the as a norm, so that's like a residual connection and a layer norm. And because of the residual connection, it's important that the dimension basically always stays the same. I mean, you could do this differently, but usually for every block, the dimension stays the same. Okay. Then, yes, how do we train without labels? The way that it was done first was autoregressive, so by just predicting the next word. So if you want to do this with attention, is this in here? Right, you need some kind of mask, because transformers are inherently bidirectional. Predicting the next word is trivial because it basically already sees the next word. So to overcome this, they basically artificially set the weights to 0. So they set alpha ij to 0 if j is larger than I, so that no information from the right can flow to the left. And if you want to train a generative model, this is necessary. So all the GPT models are basically trained this way. So ChatGPT, that I assume everyone knows, is basically trained this way, but always predicting the next words, and also like 100 million other tricks. But if we just want to learn representation, this is not very good. Because if you want to answer some questions then about the first word in the sentence that might relate to like later words in the sentence, so you want to always have the bidirectional context. So we cannot learn autoregressively. So we will use pretext tasks, basically like with images, but we have to use other pretext tasks. And the first one is mask language modeling. We basically just remove some input tokens and then try to predict them. So the idea is, if we can do this accurately, then we somehow understand the language. Originally, this was called the close test, which was something of a concept from like psychology from, I don't know, 70s, to test if someone was somewhat fluent in a language. So I assume everyone here speaks English, I hope. So can you tell me which words there are probably missing here?
Shop.
Sorry?
Shop and wallet.
What? Sorry.
So the answer is shop and wallet?
Ah, shop. Ah, I don't know, wallet is...
Umbrella.
Yeah.
And worse than AI.
Okay, you failed the human AI test. Of course, there are like different words here. It could be a store, it could be shop, it could be market. There's usually not a perfect answer, but if you can get it right, you probably have understood something about the language. So how do we do this in practice? We introduce the mask token, and we just remove some words. Then we take the representation of this masked token, because remember, each token gets its own representation at the end, and just put a linear layer on top of that and then try to predict this. So we only have a finite number of tokens. So from the example from above, the word piece tokenizer with like 30,000 tokens. So this would be a linear layer from, I don't know, if D is like 1024, from 1024 to 30,000, which we would have to learn. Just normal with cross entropy. And there are the usual hyperparameters that are chosen, and as I say usual, they're basically always chosen. We select 15% of the words that we want to mask, but then we don't mask every one of them. Why might it be important that we don't actually mask every one of these words? Can think about how then the training input would differ from the test input, basically, from the actual downstream task inputs. Yes?
If you use mask, kind of the academic training is a kind of bias. It's always going for this token as something for predicting, right?
Yes.
The system is going to have the model has a tendency to lean towards guessing, but if you put the original word here, it's kind of a bit of
yeah. So the basic is also just like the masked token never appears in the actual text. So to better represent the downstream task, then we just leave some of the words unchanged and replace some with random tokens. Yes. And then we only predict the tokens that were selected at the beginning. So this is different, basically. It sounds a little bit like a denoising autoencoder. We put noise on there, masked, and then we reconstruct basically the input. But we only actually predict on the 15% of the selected tokens. And we only predict using the embedding for this particular token. So it's a little bit more like, I don't know, like a masked autoencoder, which you will learn about later in the course. Yes?
I don't really get the last bullet point. Why are we going to leave a 10% change? We can just increase or decrease our 15% of tokens for masking at the beginning and just delete this bullet point.
No, because only the selected tokens are given to this prediction layer here. That means that sometimes this way, the prediction layer will get the input that is already correct. So that is actually different in this way.
All right.
It's also to prevent it to just only basically predict common words. Because if you leave this out, and basically if this is too large, then a good strategy is to just predict common words, and you're right kind of often. Okay, and the other pretext task that is used is next sentence prediction. So it is a little bit more long term. So you need to understand multiple sentences and their concept at once. The question is, does the second sentence follow after the first sentence? So Paul went shopping, he bought a new shirt, makes sense. Buying a shirt and shopping is connected. Second sentence is Ramona made coffee, vanilla ice cream cones for sale. Okay, both texts have something to do with food, but otherwise they're not connected. It's a non sequitur. This is not a perfect yes or no question, there's not a perfect yes or no answer usually. Of course, sometimes in real text there are non sequiturs where it's not clear how or why the next sentence follows on the first, but usually it's also quite good. So how do we do this in practice? We add more special tokens. So we had the mask token before, now we have the class token, CLS, and the separator token, SEP. The class token is added at the beginning, and the separator token is added at the end of sentences. And then they also get some number. And because this is not a token level task, we only want to predict yes or no. It's a binary classifier basically. We predict it on the embedding of the class token. So the embedding of the class token is basically that Z0 that I talked about before. The embedding of the class token should contain basically everything about the task, and we'll use this embedding if we want to do non-token based tasks at the end. Yes. So the separator in the middle is of course important, so the model knows which is the first sentence and which is the second. But even if we don't use next sentence prediction, the separation token at the end is very important for like a more technical training reason. Anyone have maybe some idea? What do you think we do? You know, we usually want to batch our inputs, right? We don't want to just have one example. This is inefficient. But if our texts have different lengths, we need to somehow make them the same length so it works. Yes. You want to?
We use padding.
Yes, we use padding. Basically, then the separator token at the end tells the network, here starts the padding, you don't need to pay attention to the rest. In practice, we usually also give the model some padding masks, so we don't compute attention between a padding token and a non-padding token, but it's also important for this. Okay, and that are basically the two pretext tasks that BERT uses. And especially this one, the masked language model with these particular hyperparameters, is used a lot. And I know maybe some people should investigate if other hyperparameters might be better, but no one has really bothered so far. They seem to work. Okay. Now what's still missing? How do we turn tokens, so integer numbers between 0 and let's say 30,000, into vectors? And the answer is we just learn it. So basically we learn for each token a vector in some dimensions, and we train this with gradient descent like before. So you can basically imagine this like you have your tokens from 0 to 30,000, you encode them one hot, and then you put a linear layer on top of that. And why do you think learning such an embedding vector is better than just using the one hot encoding? So we have our one hot token encoding, let's say, and then we learn a linear layer. So here's the idea, it's one hot, so it's a vector that is only one point, zero everywhere else, and it indicates which token it is. And then we compress it basically with a linear layer in something smaller. Of course, the one advantage is it's smaller, it's computationally more efficient, because that's the dimension that we're carrying through our whole network. But what's another reason why we don't want one hot inputs. Yes?
The output can somehow be more explicit, and you can include the context or like different uses for the same word.
Yes. Then Vic?
If you use 100 vector, also not going to be orthogonal, right? When you
Yes.
take a inner product, then you will not care anything. But if you somehow express with other fields, you like to use similarity in this attention. But 100 vector mathematics is impossible.
Yes. I mean, okay, I guess the attention would still work because before you compute the attention, you apply another matrix anyway. But yeah, the point is you learn similarity between words. Hopefully at the end, words that have similar meanings or somehow semantically connected should have similar embeddings. So that's why we learn that this way. But that's of course not enough. Transformers have no inherent concept of order. And of course the order in a sentence is very important. You can't just scramble a sentence and expect it to have the same meaning. So that's why we add this position embedding. Basically, we for each position in a sentence, we add a number, and then we embed this as well. Yes?
For which reason are we learning this embedding just linear?
Because more is just not necessary. I mean, you can basically at any point replace the matrices with some more complicated layer, but it turned out leaving this simple and everything else simple and just making network deeper is at the end more efficient. Yes?
What is this segment, type of segment?
Yeah, I'll get there in a minute. First about the position embedding. If we do it this way, like BERT does, that means we have inherently a fixed number of positions that we can embed. So let's say we choose some number, like 10,000, and then we only can embed positions from 0 to 10,000. And if we have some sequence, input sequence that's longer, then this just doesn't work anymore. So there are different ways of doing position embeddings that don't learn stuff, like sinusoidal embeddings, which you use like sine and cosine stuff to give a unique embedding to each position. But this way you're limited to a certain number of positions. Okay, and finally the segment embedding. BERT uses the next sentence prediction pretext tasks, and this mask basically tells the network which part belongs to the first sentence and which belongs to the second sentence. So there you only learn two embedding vectors basically. Right? And you might say this is not necessary because you already have the separation token. The network should already know which is the first and which is the second sentence. But again, it just turned out it learns this way faster and nicer. Okay, now we have three different embeddings. The basically most important one, the text embedding and token embedding. One embedding for each token, the position embedding, one vector for each possible position, and the segment embedding, one vector for each possible segment. And then, you can already see it, we add them all up. Why do we do this? Why do we add them, and why is this not a problem? We could also just concatenate them. Yes?
I think because it's so high dimensional that there's enough redundancy.
Yes.
Yeah.
Yes, that's because why it's not a problem. If you have two random vectors in high dimensions, they're basically almost guaranteed to be orthogonal. So if you add them here, there's not much risk of collision. Then of course, if we just concatenate them, we would have a huge vector at the end. We don't want this. This is slow. Also, just as we want to learn correlations between similar words, we might also want to learn correlations between words and positions. Maybe some words, if they appear in at the first position, like the, should have some special correlation there. If we learn them independently and just stack them, the learned position vectors and token vectors would always be orthogonal, so there would be no information flow between them. So that's why we just add them up. And then we usually also apply some form of norming afterwards, typically layer norm. Okay. By the way, this week's exercise will be BERT, so you will implement some small version of BERT. And then there's, again, explained somehow a little bit, and you need to implement this here. Okay, then if we put this all together, we get BERT, which stands for bidirectional encoder representations from transformers. Again, like all the popular machine learning methods, they somehow smash words together until they have some nice acronym. But the important part here is bidirectional. Because even though it's not like the first time transformers have been used on language, it's the first time that I said, why do we actually read this from left to right, when we can read it both directions together? GPT, like the precursor of ChatGPT, was trained with transformers before BERT, but only like one directional. Of course, GPT is inherently like a generative model, so it needs to be learned this way, but well, anyway. So BERT was trained using these two pretext tasks, next sentence prediction, and masked language modeling. It has the transformer architecture. The large BERT had 24 layers, hidden dimension of 1024, 16 heads, so total parameters 340 million, which is not very big in today's standards. Does anyone know what ChatGPT 4 is about in number of parameters? I think it's already in the trillions. So this is not much, and it's not even so old, but it was trained on the books corpus, which is books, total 800 million words, and the whole of English Wikipedias, which is like 2.5 billion words. And because it uses this next sentence prediction, it's important that it actually uses some large contiguous text from which we can draw next sentences. Okay, how do we evaluate? How do we evaluate our network? What are our downstream tasks? It's basically, again, linear probing. We put a linear layer on the top and do whatever we want with it. But what's important with BERT, they fine-tune the whole network. They don't just train the last layer, they fine-tune the whole network with a small learning rate. Which of course takes a long time, but yields a little bit better results. You can also just but you can just not do that. You can just use linear layer, which is faster. And the weights of BERT and the other variants that I will tell you about in a minute are freely available from like Hugging Face and wherever. So if you want to do some language stuff, you can just use this, put a small network on top, and you're good to go. And it's evaluated on the CLUE benchmark sets, which I forgot what it stands for, so in the PDF that I will upload later, there's a link there. I think it has like 17 tasks in total. One of them is this COLA tasks, where you have sentences, and the task is to say which of these sentences makes sense. Okay, who thinks the second sentence makes sense? No one? Good. Some of the sentences are very obviously nonsensical for humans, at least. Some of them are a little bit more tricky. They're all also available in Hugging Face, so if you want to take a look and investigate what these datasets look like, you can do this. Other one is the RTE task. This stands for something entailment, which is the question, does the second sentence entail from the first? So does the second sentence follow from the first? In this case here it does. So something about Pope dying, and then the new installation of the Pope Benedict XVI. And the second sentence is Pope Benedict XVI is the new leader of the Roman Catholic Church, which is already kind of complicated to understand that this entails from the first, because you kind of have to understand that the Pope is the leader of the Roman Catholic Church, and complicated words like installation and such. But like there are lots of other tasks, and BERT did quite well. So this is just the table directly copied from the paper. Do read the paper if you're interested. Important is mostly just here the last line, GPT, which is a transformer model with like the same number of parameters as BERT base, but it outperforms GPT in basically all tasks. So like especially the polar task and the RTE tasks has like pretty big improvements. Okay, what's this? Okay. Then there are lots of BERT variants that have also BERT in the name. Like Roberta, for example, which is basically the same as BERT. It has different training parameters. It does not use the next sentence prediction task, only the masked language modeling task. So it turns out we don't need next sentence prediction anyway. We don't need it, but you will need to implement it anyway for this week's exercise. The most important changes were just bigger batch size, longer training, more data, and it got better results. And then Albert and Distilbert, which don't perform quite as well, but are much smaller and faster. And basically everything I said so far can be applied to any other number, any other kind of sequences. So DNA, for example, for DNA there's DNA BERT, for RNA there's RNA BERT, and there are other sequences, I assume, for which this is used as well. Of course, especially for RNA and DNA, this makes much more sense than some autoregressive way, because in language at least there is a canonical direction from left to right, even though it's like the last word can be important for the worst, but like in DNA the direction is like more complicated, I guess. It doesn't have like a real left to right direction. And these DNA and RNA models also use like the same hyperparameters for masked language modeling. So 50% selection and 80% masking, because it just works. So far no one has like figured out a better way to select those hyperparameters. Yes, and again I'm too fast apparently. It means you can get more next week. Though here's some further reading if you want, and especially recommend this Transformer blog post, which is actually written from Nicholas, by Nicholas. Yes, are there any more questions regarding this lecture?
So what's this BERT used for? I didn't get it.
Basically for everything language related. you want to have some sentiment analysis on tweets, for example. You want to scrape like all tweets that have like the hashtag 22 election or something, and you want to know which have like a positive sentiment, which are like positive and which are negative. You could like scrape all the data and train it on this whole big network on this, or you could just take your BERT embeddings. You could use a pre-trained BERT network and then just train a small linear layer on the embeddings.
But would it also work like with ChatGPT, or does it also generate?
No, it does not generate. So it's only for representations, basically.
And it works only for English. If you said that so the source of the data was Wikipedia and books, and also like why there are no, let's say, dialogues in the training videos. For example, I think I've heard about some Polish, because I'm Polish, so there was such a Polish project, and they now gathered the data to also create whatever, and they, for example, also use like subtitles for movies because they want this dialogues kind of things.
Yeah. Yeah, even if it's only trained on English, then it's only going to learn English. Of course, in books and like novels, there's already a lot of dialogue, so it kind of learns that.
Yeah, okay.
But of course, learning multiple languages at once is complicated because there's lots of, you need like a lot more data because you actually want to learn that maybe one word in Polish or English means the same in another language, so it should have a similar embedding, but it's very difficult to learn if your texts have only English and texts have only Polish. So you want to have texts that have like multiple stuff. So you need a lot more data. And like some of the follow-up things of BERT use different languages. I think Roberta used multiple languages, I'm not sure. And like there are a lot more variants of BERT, and you can look at them here at this link. And some of them use different languages, but yes, the training data and language is very important. But it's possible to learn multiple languages at once. I assume most of you have played around like with ChatGPT, right? And this is pretty good at multiple languages and even translation. Like not perfect. And of course it's trained differently, but just because there's such access to such a huge amount of data.
Thanks.
Right. Anything else? Anything not regarding this lecture, last lecture, or anything? Okay, then I think we don't have a problem with that end lecture now, and we'll do the exercise in 11 minutes and 4:15. Right?